All right, welcome to hypothesis testing with proportions. What I'm going to do with this section is trying to introduce you to the concept of what were we actually trying to do when we run a hypothesis test. And a hypothesis test is something that typically any major in any degree at some point will come across. You will see things such as p-value and null hypothesis and alternate hypothesis, these types of things in research articles that you may go through, or you might actually conduct the research on your own. But the main concept of any hypothesis test is the same, and that's what we're going to try to go through here. So in our previous section, previous unit, we talked about confidence intervals. And what confidence intervals were is confidence intervals were a way to approximate an average based off a sample. Well, this is going to be a little bit different, using a lot of the same tools and the same mathematics, but the concept is different. What we're trying to do here is we're trying to determine whether or not a sample that we take is significantly different from a population sample that is known. And the reason we're doing that is we want to see if there's any change or there's any difference in what we have done within our sample versus what the known sample should be. So for example, the one that I'm going to use is just some information I found online, which is 82% of students nationally graduate with a four-year degree will be employed within a year of graduation. When I looked up Nazareth College, you had 562 students graduate, and 498 people had, or students had jobs within a year of graduation. That puts Nazareth at around 89%. So the question is that 89% just a difference in sampling? So if we went back the next year and you have 472, does that go below 82%? Is it going to, I mean, obviously this will vary. This number is not going to be exactly 498 out of 562 every year. But the question is this significantly different than 82%, or can this just happen differently from by the way we sample? So what I'm going to do is I'm going to bring over this next page, just kind of show you what it looks like on a bell curve. We've done so much stuff with bell curve, and here are some kind of big ideas that I want to go through with this bell curve and what we're doing. So the sense is this: 82% is what they told us. They told us, or in our research, we found that 82% of students will graduate with a degree and have a job. Nazareth is 89%. So the question is, where does this 89% fit in? And what we try to find, the main calculation we're trying to look for in this case is a p-value. And that p-value, what the p-value determines, is the p-value is going to determine what's the probability of this happening. So I'm moving this around because I want you to see it. What's the probability of this happening by chance? And the way we do that is we set up what we call a critical region. This critical region I highlighted in yellow, and you'll notice I only put it on one side of the curve because the only thing that Nazareth cares about is, are we doing better than the national average of 82%? So that's why we call this a one-tailed test, is we are only looking at, are we better than 82%? We said, are we different from 82%? That would be what we call a two-tailed test. A majority of what we're going to be doing is a one-tailed test where we're going to be looking at just one side of that bell curve. And that's true in most situations. You generally have an idea going in, or your own thoughts going in. You're trying to determine whether or not something's greater than a number given. That's more typical than any other situation I've seen. So most of the situations we're going to look at are one-tailed. Now, we define this critical region as a percent. And what we're saying is, if 82% is a real number and we take a sample, what's the probability of us getting into here? So what's the probability of our number happening? So in this case, it's the 89. What is the probability of 89% happening in our sample like we got with our Nazareth sample? So the p-value, and don't worry about all the calculations. I'm going to show you how to do the calculations later, but I want you to understand the concept first. The p-value is what is the probability of this happening? And we're going to set up a critical region. So if this number is over here, so let's say we get 89% for our sample. Let's say, for example, this percent is around 15%. So if we just were to draw a line here, we'd look at something, in the neighborhood of, let's say this is 15%. So let's say 15% of the time, we'll get a number like 89 if the real number is 82. Well, you notice we haven't really crossed this threshold yet. We haven't crossed this threshold of the 5%. So in that case, it's really not different from the 82%. How would it be different from the 82%? will be different from the 82% if it was in that critical region. So if it ends up in that critical region, which means it happens less than 5% of the time, what we're going to do is we're going to say, yes, it's significantly different from the 82% because it's so much greater. So that's what we're going to do is trying to find a measuring stick, trying to find a tool to measure. And we call that tool the p-value, which is the probability of this event happening if 82% is a real number. So how far away are we? And you should be thinking in your head deviations and z-scores, which is really what we're going to do when we calculate our p-value, is based on our sample, what's the probability of 89% happening? And again, if it happens less than 5% of the time, we are going to say it's critical and it's significantly different from the 82%. If it doesn't happen less than 5% of the time, we're going to say it's not significantly different from the 82%. So again, we define this area, the shade in yellow, as a critical region. Now, I put a 5% here. Just like in confidence intervals, when you have 99, 95, 90% typical, you could also change this to say 10%. Now, it would give you a wider region, so it would give you more area. So it would be easier to fall into that critical region and say it's different. Or you could even move it all the way out here, and instead of 10%, change it to 1%. We can really define we want this critical region to be. We can say if it happens less than 1% of the time. So, for example, if it's here, no, but here, then it's significantly different. So we can define that level of significance in this critical region, and we're allowed to define that. And typically, this is defined by how serious this is. So in most situations where it doesn't really matter, it's not a matter of life and death, or maybe our business going bankrupt or something, we're going to stick with 5%. If it's a serious matter, like if you look at the coronavirus and everything going on with that, well, those are more serious. We want to be more sure. So, for example, in that case, we want to start flattening the curve and releasing people back into the normal world. We might want to wait until this hits that 1% for our critical value. If it's something like this, we're just saying, is Nazareth different? We're going to stick with, say, the 5%. Now, you also see here the HO and HA. So what the HO and HA are is our null and alternate hypothesis. So if you go back and look at this page, the null hypothesis is the population that we are interested in testing, and the alternate is the other side of this. So what are we looking to test? In this case, the null hypothesis is 82%. And the null hypothesis is always going to be, what does your population tell you? In this case, it tells you we are at 82%. The alternate hypothesis is what you are trying to prove. So the alternate hypothesis in this case is that we're greater than 82%. We can't technically say it's going to be 89%. We have no idea what Nazareth's numbers are. It could be 89% one year. It could be 92% the next year. It could be 84% the next year. It's going to vary. We don't know what the average is, but we don't care in a hypothesis test. What we care about in a hypothesis test is this large enough to say it's significantly different, that we are better than the 82%. Then if we want to later on, we can create an estimate where we are using a confidence interval. But for right now, we're just looking at, are we significantly different than the 82%? It's the only question we care about. Are we significantly different than the 82%? So again, the alternate hypothesis is that we are greater than 82. The null is that we are equal to 82. So what I'm going to do now is I'm going to stop this video. Hopefully you have some good notes, and then what we are going to do from there is I'm going to give you a video showing you the mathematics that go through this.